In this lecture or in this module, we will try to learn the concepts of series of real numbers, their convergence. To study the convergence of a particular series, we will discuss a few tests, and those tests will be used to judge whether a series is convergent or not. If it is not convergent, then whether it is oscillating or it is divergent, whatever it may be, can be judged by these tests. And once we get this, we will try to find a necessary condition for the convergence of such series. We will show that this necessary condition may not be sufficient, so we need some more other conditions to check whether a series is convergent or not. Then once we go through the convergence, then we will describe two important theorems based on the rearrangement. Though the proof of all the theorems that we will be discussed in whole lecture are beyond the scope of this module, it can be found in any standard textbook or material available on real analysis. A series of real numbers is an expression of the form a1 plus a2 plus a3 and so on, or we write in a very compact form sum over n from 1 to infinity an. This is called a series of real numbers where a1, a2, a3 all are real numbers. For this series of real numbers, we define nth partial sum as Sn. It says I from 1 to n sum over I from 1 to n ai. So we are adding first n elements. It is a1 plus a2 plus a3 plus an. So if you take n equals to 2, that means we are talking about a1 plus a2. If I take n equals to 3, that means it's a1 plus a2 plus a3. A series n from 1 to infinity an is said to converge. It will converge to some real number s belonging to the real line if the sequence of partial sums converge to s. So that is very important. We have to find the partial sums and then we have to construct the sequence of partial sums. Then we have to judge the convergence of this sequence of partial sums. If they converge to s, we say the series converges to s. If Sn converges to s, then we write sum over n from 1 to infinity an is equals to s. A series which doesn't converge is called a divergent series. A necessary condition now we will discuss. We are talking about a necessary condition. We will show that this condition is not sufficient. That means if a series converges, then it has to obey or follow this condition. But following this condition will not suffice for the convergence. So we write if n is equals to 1 to infinity an, this series converges, then an must be converging to 0 as n tends to infinity. Converse may not be true. The proof is not very difficult. You know an can be written as Sn minus Sn minus 1. Take n equals to 2. a2, how to get a2? Now I can write a2 as s2 minus s1 because s2 is nothing but a1 plus a2 and s1 is a1. So s2 minus s1 says a1 plus a2 minus a1. So a1 gets cancelled and we are left with a2. Similarly, I can construct a3, a4, a5, a6 in this way as the difference of Sn minus 1. The condition we are given that sum over an converges. So by definition, if they are convergent, then Sn and Sn minus 1 both will converge, and Sn and Sn minus 1 both will converge to the same number. So an tends to 0 as n tends to infinity. Now the question is that whether the converse is true or not. That means if an tends to 0, then whether the series is convergent or not. Let us consider the counter example. We are talking about the series n from 1 to infinity 1 over n. The above series is divergent, but 1 over n tends to 0. So this condition is not sufficient, it is only necessary. Now we have one important theorem. Suppose an is a sequence of positive terms such that an plus 1 is greater than an for all n belonging to the set of integers, then the series sum over an diverges because the series is expanding. An plus 1 greater than an means a2 is greater than a1, a3 is greater than a2, so we are getting larger real numbers in that sequence. So it is expected that the summation will diverge. Consider an as n over n plus 1. So what is n plus 1? An plus 1 is nothing but n plus 1 over n plus 2, and it can be shown quite easily that an plus 1 is greater than an. So the sequence or the series n over n plus 1 sum over n from 1 to infinity, n from 1 to infinity n over n plus 1, this series diverges. Now we will consider one very important series called geometric series. Let us consider the geometric series of the form a q to the power n minus 1, where sum over n from 1 to infinity, and a is not equals to 0 and q belongs to the real number set. So we can write Sn as the nth partial sum as aq square, aqq plus aq to the power n minus 1 for all n belonging to capital N. Now if a is equals to 0, then we don't have to bother much because Sn equals to 0 for all n. Then what will be Sn? Sn will be Na if q is equals to 0, because all the time we will be having a. So there are Na, so Sn will be Na. If q is not equals to 1, then we can use the formula and we can write Sn as a into 1 minus q to the power n over 1 minus q. Now what will happen if q is equals to 1? If q is equals to 1, the series is not convergent because Sn is not bounded, because Sn is a into n. As n increases, Sn will also get increased. If q is equals to minus 1, then also Sn diverges. Then Sn will be a if n is odd, and if n is even, then it will be 0. One interesting feature is q is not equals to 1. Then mod of Sn minus a over 1 minus q is mod a over mod 1 minus q and mod q to the power n. This implies that if mod q is less than 1, the series converges, and if mod q is greater than 1, Sn is not bounded and hence it diverges. So depending on the value of the mod q, the series either converges or diverges. This is very important result corresponding to geometric series. Now we will talk about more results in convergence of the series. Suppose we have two sequences an and bn such that for some k belonging to the set of natural numbers, an is equals to bn for all n greater than equals to k. So k can be any number, any real number, any integer, it should be integer. Suppose if n is greater than 10, k is 10, and we are saying from 10 onwards all a values are equals to all b values, then sum over n converges if and only if sum over bn converges. We are not going to prove all these theorems that we will be stating, because most of them are found in any standard textbook of real analysis, and this is beyond the scope of this lecture. If we construct a series Bn sum over n from 1 to infinity by adding or omitting a finite number of terms to sum over n, then sum over n converges implies and implied by sum over Bn converges. Particularly sum over n from 1 to infinity an, if this converges, this implies and implied by that sum over n from 1 to infinity an plus k also converges for any k belonging to n. So even if we are omitting finite number of terms, the convergence will not be affected. Now if we have two series n from 1 to infinity an converges to s, and sum over Bn, n from 1 to infinity converges to t, then for every alpha and beta belonging to the real line, that means they are real numbers, then the series n from 1 to infinity alpha an plus beta bn converges to alpha s plus beta t. Now whether a series is convergent or not, we will go for some tests. Now I will describe the tests that are available to test or to judge whether a series is convergent or divergent. So the first test we will be talking about is called comparison test. Suppose an and bn are sequences of non-negative terms. So this comparison test will be applicable only for non-negative terms, and an is less than equals to bn for all n. So if bn converges, sum over n from 1 to infinity bn converges, that implies sum over n from 1 to infinity an will also converge. And if an diverges, that is sum over n from 1 to infinity an diverges, then sum over n from 1 to infinity bn will also diverge. One important corollary is that suppose an and bn are sequences of positive terms, and suppose L is equals to limit n tends to infinity an over bn exists, then if L is greater than 0, then we say that sum over bn converges implies and implied by sum over an converges. If L is equals to 0, then we say that if sum over n from 1 to infinity bn converges, that implies sum over n from 1 to infinity an also converge. The second corollary that we have, that if limit n tends to infinity an over bn is equals to infinity, that means if sum over an is converges, that implies bn also converge. Now this is called comparison test. So if you want to find the convergence of a particular series, you have to compare it with a different series. So this is the question we will be asking: the series 1 over n factorial n sum over n from 1 to infinity, whether this series is convergent or not. Note that 1 over n factorial can be written as 1 over n factorial less than 1 over 2 to the power n minus 1 for any n. Take any value of n, obviously the integer values, then this condition will hold. Now we know that 1 over 2 to the power n minus 1 sum over n from 1 to infinity, it converges. So by comparison test, n from 1 to infinity 1 over n factorial also converge. Similarly, if we consider the series n from 1 to infinity 1 over square root of n, whether this series is convergent or not. Now I can see that 1 over square root of n is always greater than equals to 1 over n, and we know that sum over 1 over n is divergent series. If this is divergent and 1 over square root n is greater than equals to 1 over n, that means 1 over square root of n is also divergent. So these two examples they use the method of comparison test to judge whether a series is convergent or not. We can have some other tests too. The next test we will be considering is called D'Alembert's ratio test. Here we don't need any second sequence. Suppose an is a sequence of positive terms, so this test is valid only for the positive series. So positive terms such that limit over n from n tends to infinity an plus 1 over an is equals to L, and this limit exists. Then if L is less than equals to 1, we say the series is convergent. If L is greater than 1, we say the series is divergent. But this test is silent whenever L is equals to 1. We will be discussing the case L is equals to 1 later on. The next test we will be talking about is called Cauchy's root test. Suppose an is a sequence of positive terms such that limit n tends to infinity an to the power 1 over n is equals to L exists. Then just like D'Alembert's ratio test, here we also have the same condition, that if L is less than equals to 1, the series converges. If L is greater than 1, the series diverges. These tests, just like D'Alembert's ratio test, keep silent in the case for the case L is equals to 1. After knowing these three tests, now we will check the convergence of a few series as a case of examples. As the first example, consider the convergence of the series sum over n from 1 to infinity x to the power n over n factorial, where x be any real number. Then an can be written as x to the power n by n factorial. Now if we take the ratio an plus 1 over an and we take the limit n tends to infinity, then it boils down to x over n plus 1 and limit n tends to infinity. Now as n tends to infinity, this term goes to 0. So by D'Alembert's test, this series is convergent. For the second example, consider the series sum over n from 1 to infinity n over twice n plus 1 to the power n. So this is my n by twice n plus 1 to the power n. So if I take the 1 by nth square root, that means an to the power 1 over n, and just check the behavior when n tends to infinity, that means I am taking the limit n tends to infinity. We are left with limit n tends to infinity 1 over 2n plus 1, and this is less than half. So by Cauchy's test, this series is convergent. As a third example, consider the series 1 over n into n plus 1. Now if you see the nth partial sum Sn, this can be written as sum over k from 1 to n 1 over k into k plus 1. Simple mathematics says it is nothing but sum over k from 1 to n 1 over k minus 1 over k plus 1. So that means if you put k equals to 1, that means 1 minus half, then put k equals to 2, that means half minus 1/3, so it will be 1 minus half, again plus half minus 1/3, again plus 1/3 minus 1/4, and so on. So we will be left with 1 minus 1 over n plus 1, and if you take the limit of the nth partial sum, it will goes to 1. So that says that the series is convergent and it converges to 1. Now we will define absolute convergence. What do we mean by absolute convergence? A series sum over n from 1 to infinity n is said to be absolutely convergent if the absolute value of the series we obtain by taking the absolute value converges. That means sum over n from 1 to infinity mod of an converges. And one very important thing is that every absolute convergent series converges. That is quite natural. A series sum over n from 1 to infinity is said to converge conditionally if sum over n from 1 to infinity n converges but not absolutely. So we will take few examples to define what we mean by conditionally convergent and absolutely convergent. Now the first series we take minus 1 to the power n plus 1 over n, sum is from n from 1 to infinity. This series is conditionally convergent. But if I take minus 1 to the power n plus 1 over n square, this series is absolutely convergent. Same with the series sum over n from 1 to infinity minus 1 to the power n plus 1 over n factorial. This is also absolutely convergent. The proofs of this, whether it is absolutely convergent or conditionally convergent, is not very hard to get. Now we will discuss two important theorems. Only we make the statements. Proof of these theorems can be found in any advanced level book, textbook which are available and beyond the scope of this tutorial. You will find the proof in any tutorial which relates to real analysis. Suppose sum over an from 1 to infinity is absolutely convergent series and Bn is a sequence obtained by rearranging the terms of the sequence an. So an is my previous sequence and we are making a new sequence by rearranging the terms. Then sum over Bn is also absolutely convergent. If sum over an is absolutely convergent, and sum over n from 1 to infinity an will be same as sum over n from 1 to infinity bn. So if we have an absolutely convergent series, and after rearranging we are getting a new series, then the new series will also converge. Suppose sum over an is conditionally convergent series. So now we are talking about conditionally convergent series. Then for every alpha belongs to the real number, that means alpha is real number, there exists a sequence Bn whose terms are obtained by rearranging the terms of an such that sum over Bn will be equals to alpha. So we can have this rearrangement theorem for conditionally convergent series too. But the proofs are beyond the scope of this lecture. We will discuss one important application of this theorem for this example. We are considering the conditionally convergent series n from 1 to infinity minus 1 to the power n plus 1 over n. Note that this series is conditionally convergent. We can rearrange the terms as 1 minus half minus 1/4 plus 1/3 minus 1/6 minus 1/8 and so on, and in general we can write 1 over 2k minus 1 minus 1 over 4k minus 2 minus 1 over 4k and so on. So this is the rearranged series from the series we have. This rearranged series sum over n from 1 to infinity bn, we can find the convergence and we can show that this converges to some alpha, and we can find that alpha 2. So this is the hint, and if we proceed in this way we can find the limit. Now after defining the definition of series and convergence, we are being able to check whether a series is convergent or not using a few tests that we have discussed. So if we use those tests, we can, on the basis of the result of those tests, we can say whether the series is convergent or not. This convergence of this series will be extended in my next module to the convergence or series of functions. So before going to the series of functions, this is the fundamental thing that you need to know.